Welcome to the Bug Bash podcast, where we talk about all things software correctness and reliability. I'm your host, David Wynn. Some bugs are so rare, they can take years to track down and fix. But what if you could find and fix 5 of them per day? For Joran Dirk Greef, the creator of the TigerBeetle database, that's not a wild dream. It's how his team works every day. While most people think that building a new database takes a decade, Joran's team built TigerBeetle in just 3.5 years. The key is a unique philosophy for writing software called Tiger Style. Joran joins the show to share the secrets behind their speed and safety. You'll hear why he thinks picking C would have been a fatal mistake, how a strict rule about memory can force you to write better code, and why Zig was the perfect choice for TigerBeetle. The key to it all is a powerful testing method that Joran calls existential for any important project. If you want to hear more about how his team turns squashing impossible bugs into their normal day-to-day, stay tuned. Hello, everyone. Welcome to the Bug Bash podcast. My name is David. I'm your host today, and I am joined by my co-host, Richard. Richard, would you please introduce yourself?
Hey, I'm Richard Hart. I'm a principal engineer at Antithesis, and specifically, I'm the architect for our fuzzer and pangolin, which is our new database.
Excellent. And we are joined today by our guest, Joran Dirk Greef. Joran, please do your best to introduce yourself, because I didn't want to take that one on. It seemed like you've got a lot of accolades that would take me a long time to read.
Well, thanks so much, David, Richard. Pleasure to be here with you all. And my name is Joran. I created TigerBeetle in July 2020 as the world was going into lockdown. A difficult time, and created something. That was TigerBeetle. And now founder of the company and sort of architect. But yeah, pleasure to be here with you. With big fans of Antithesis, as you all know, and follow the Antithesis journey. I think I was knocking on the door of Antithesis before there was even a sign hanging outside. Saying, well, can we come and be a customer? You know, he said, yeah, you can be our lucky 13th. So that's perfect. I don't know how much I can disclose, actually. Maybe I have to edit that out.
That's okay. We'll fix it all in post, or we're going to leave this in because people love behind the scenes type stuff.
Awesome. So, yeah, we had, just wanted to pick your brain about TigerBeetle, and specifically the lessons that you learned that led to TigerBeetle and what you've learned while developing TigerBeetle. So I guess starting in no particular order, it feels to me like over the last decade or so, maybe a little longer, there's been a big increase in techniques and knowledge around how to develop software more effectively and more efficiently. So I'm curious, like, what database features, or more generally, what software functionality do you think has been enabled by things like more, quote unquote, modern programming languages, or, better increases in testing sophistication and yada, yada, yada?
I think that sort of speaks like to the history of TigerBeetle. So going back to July 2020, or go back, 10 years before that, I was following the FAST storage conference, which is a conference all about, doing distributed systems and storage and file systems. If you squint, it's databases. I always believe that, a file system is a database, or a database is a file system. And so I was following the FAST conference for many years. And the reason I mention it is because at that conference, there was all these papers coming out year after year after year from University of Wisconsin-Madison. And it was Professor Ramsey Apache-Dussault and his wife, Professor Andrea Apache-Dussault. They authors also of Operating Systems 3 Easy Pieces. I'm a huge fan of that book. It's one of my favorites. I actually wrote to them. I said, to me, it beats KNRC. So like that's really my favorite is OSTEP.
I have it sitting on the shelf at home.
Oh man, great. So much fun in that book, and bring all the research alive. But they were publishing these papers at FAST. And the reason why I mention it is because they were showing that most storage systems are not correct, because most storage systems sort of assume that the hardware never fails. The disk is always perfect. And they were showing this, but also showing how you could design systems that would be like RAID, where they can repair, except they're like distributed RAID. I was a huge fan of ZFS, and ZFS had kind of done this in a local context. But I got so excited about this research because I thought, wow, like there's no database out there today that, if they have checksums, they're disabled by default. That's like the industry's default setting is the checksums are disabled. Or there aren't checksums, or like SQLite's documentation says what we read from the disk is what we wrote, like verbatim, that's from the docs. And there's nothing wrong with that. It's just that 30 years ago or 20 years ago when these databases were designed, this research didn't exist. So in those days, it was just assumed that you trust the file system. The file system people are like, no, well, we trust the block device. The block device people were like, well, we trust the firmware. The firmware people are like, well, and it's corruption all the way down. And here at FAST was like new research saying, well, actually, we can apply the end-to-end principle. And it's going to be much better because now you don't need to run expensive RAID locally, for increasing your storage costs. Now you've doubled your disks. Actually, we have these distributed systems. They do replication. They have copies of the data, but our consensus protocols aren't talking to our storage engines. But if they could, we could survive a whole lot of, almost near Byzantine, faults. And so I got really excited, and it really puzzled me that there was no database on Earth, as far as I could see, that was listening. No one. There were things like fsyncgate, Postgres data loss, and it wasn't only Postgres; it was MySQL. I believe it was SQLite, WireTiger. Everybody would lose data through fsyncgate. Then there was the protocol-aware recovery for consensus-based storage, which is how to use your global consensus to recover from local storage faults. Basically, like how would you apply ZFS? Those learnings to a distributed database and co-design storage and consensus, but nobody was paying attention. And I thought, this is puzzling because to me, this was my passion, following all this work from them. And so speaking of, what new database features could you build today? And in 2020, that one seemed like, wow, we can take all this work. And, I wish I was kind of building a database because I would put this in. So, as it happened, I got the opportunity. And it always, I don't know if you've read Pillars of the Earth by Ken Follett, but it's the story of a stonemason, and he wanders around medieval England, and his dream is to build a cathedral, but it's an expensive endeavor. You need a patron, but he's always walking through the forests and getting inspiration from nature. Like this would be his Sagrada Familia if he built it. And for me, I was like, well, this would be the research I would want to do. And then I got the opportunity to build a financial transactions database, which was TigerBeetle, Apache 2.0 open source. But we put all this research in, and I think that was interesting because, so I guess it comes back to the question, what can you do because of programming languages? But a lot of the storage fault research, if you wanted to apply it, you needed not only to do fsync, of course, and things like that, but you also needed direct I/O. So you needed to have like more precise type alignment in your type system. All your memory buffers, you needed to start thinking of alignment. And I'd done a lot of C around this time. So when it came time to, what language would TigerBeetle be written in, interestingly too, there's so much to say on this topic, but Red Panda was coming out. So as I was designing TigerBeetle, I watched Red Panda launch. And it's interesting because they launched with C Star, C++, everything, a lot of, DPDK, SPDK, everything was user space. They had fantastic, very efficient with memory. But it was kind of it's difficult, and I thought, well, for TigerBeetle, we're going to do very similar techniques because the hardware's changed in the last 30 years as well. It's not only all the storage fault research, but disk bandwidth used to be the bottleneck. These days, it's memory bandwidth. So if you're building a database, your thing is memory. You don't want to thrash the cache. You want to do, it's very different. The whole anatomy has changed. But so you want to do things like static memory allocation, and then you've got, languages that will allocate everywhere. But so basically the choice was between C or Zig, also because we wanted to handle out of memory. But C would have been, a colossal mistake to have picked. I was comfortable in it, but that was kind of the only language that we could have built TigerBeetle in because of static memory allocation, the alignment, and wanting to handle allocation failure. This thing's got to keep running. It can't just panic if it runs out of memory. You also want to be able to know you've allocated all your memory for performance. You wanted to be able to use standard lib, where the standard lib is not just dynamically doing stuff and allocating. You want to bring your own buffer, a lot of intrusive memory patterns like that. And so actually Zig was around at the time, and I'd been following it for 2 years. And I kind of threatened people. I said, look, we're going to write it in C. And they said, no, please pick Zig because the toolchain's already better. But that's what I wanted to do, was to write it in Zig. But that's how we picked Zig. But actually a lot of Zig's features, it's very precise with crafting memory. In the type system, you can express your memory alignment for direct I/O, leads into all the storage fault work. Zig comp time also is quite amazing. We use that for our LSM. We don't have one LSM tree, which is quite typical in a database. We actually have more than 20. And we do that, using sort of meter programming, but at compile time using Zig comp time. Doing that with macros would have been a pain, So a lot of things in Zig are just very, very conducive for TigerBeetle. Could go on, but it was a good, the timing was very lucky, because I actually interviewed Alex Kajego of Red Panda, because our designs are so similar. And I said, it's almost like we're databases on two sides of the fault line, the last 30 years of systems language and the next 30, Rust and Zig. I also looked at Rust. That would have been another contender, but back to you. Yeah. Anything I can dig in on there?
It's almost like one of those things where multiple innovations with the same space of the neighboring possible sort of pop up at the same time, right? It's interesting when you talk about Zig, because as I understand it, Zig has not reached 1.0 status yet, right? So do you feel sort of the evolution of the language as you guys are putting together TigerBeetle, and does it influence how you guys implement it, or the design choices that you make under the hood, or how is it like working with that project? Have you found any bugs in Zig? Like, as we haven't talked about you guys testing practices yet, but what has that dynamic been like?
Yeah. Oh, Zig I can't tell you how much better it's been than I ever thought. So I thought it would be amazing if it takes off. And it's been so much better. And I knew in 2020, Zig's standard library was incredibly high quality. Like, if you looked at the hash table implementations, the interface design was so good. A lot of people know that with Zig, you bring your own allocator. But there's many design decisions like that in the language that show a lot of taste on the part of Andrew. And for example, like Zig's safe builds have got checked arithmetic enabled by default. If you look at other languages that are supposedly safer, if you look at their safe builds, they don't actually have checked arithmetic enabled by default, but Zig does. So it's these little things, all these little things of quality. And you could see that in 2020. And what we were careful is, we never use Zig async. We tried it out, but we were careful to stick to stable language features. So we never used the standard lib for I/O. We designed and built our own I/O stack for TigerBeetle, cross-platform, running on Windows, Mac, Linux. Bun later adopted that. And Zig is now actually adopting what's very similar to that I/O interface in the new I/O sort of advances that they're doing, which are really great, by the way, which we support. Really solving async I/O properly, because it's a very hard problem. So we didn't use Zig async because we knew it was not stable, and that because we're quite close with in the community. I think also Zig is a very simple language. It's a very small grammar. So there's not a lot of surface area where it can be unstable or the quality, there's not a lot of dusty cobweb areas. It's such a simple language that you just don't use async and make sure you own your core dependencies, and you're good. So that's what we did. And so we've never really had the velocity of this is the other way. This is how I see it, is that Zig actually brings a lot of velocity. So we needed prefetch, to prefetch memory as like a CPU built in. and we could do the PR and get it merged in like 48 hours, or I can't remember exactly how long it took. But if we were using another language, try and get that merged, it's going to take like a year. That would have been the risk for us, is that the very basic things that you just have to have, the access to the built-ins, like we can put them in. So I put IOU ring into the Zig standard library. Didn't take long, and I got it in exactly how we wanted it. Whereas if you look at other things like libuv, people were trying to get IOU ring in there for years. And it just, things move so slowly. So Zig, you've got real freedom. Obviously, there's great leadership from Andrew as BDFL. So nothing is going in unless it passes the test. And that, that IOU ring, there were like 50 commits on that. But you could make things happen. So I really loved that about Zig. Did we find any bugs? Very early on, I found one. It had to do with alignment of a 128-bit, integer. The very cool thing was I reported it. Someone else had already fixed it, and that was already merged. Again, velocity. And otherwise, the quality has been really great. I'm sure we found one or two bugs, but essentially Zig is a front end to LLVM, which everyone uses. So LLVM is probably the problem for everybody, But again, here Zig is investing, so they, multiple backends. We didn't want to pick a language that wasn't going to invest in the whole toolchain. So Zig is fantastic for cross compilation. It's probably, I think everyone would agree, from Go or from Rust, you're using Zig to cross-compile your Go or your Rust. Like the toolchain of Zig has definitely won. Like it's better than anything else. The most powerful toolchain. And so I think as like a little language, it's highly powerful. I almost start to call it, the most powerful language, just because of the toolchain. It's kind of so hard to beat, because Zig is working one level deeper. So these kinds of things I didn't see coming, that Zig was going to invest so much in the toolchain. That happened after we picked it. But now it's been 7 years. So to me, Zig seems very old, and it's still perfect. And I've never regretted it once. So really, really happy, and love the language. It's just beautiful to read. It's exactly what we want to do, and it captures that like ethos of C, which made C beautiful. I think was the simplicity and the power to weight ratio of the language. Very high power to weight ratio. You can say a lot with a little, except you're not walking blindfolded on the cliffs of Dover while about to walk into undefined behavior. Zig is far more of a spectrum. So if Rust is going for 100%, memory safety, Zig is thinking of that more probabilistically, and that's also what I like, that it wasn't extreme, but it was very practical. Like let's solve spatial safety. Let's have bounds checking. Let's do checked arithmetic, and all these things start to downgrade the probability of memory bugs into another category where you no longer worry about it. There's now much bigger bugs to worry about. So I could go on and on, but
So sorry,
you
go
might
ahead,
notice
David.
we let you go on and on here. So beware of how that
I'm not
plays out.
supposed to. Thanks.
Yeah, so I'd like to drill in a bit about this, the pattern of statically allocating memory at initialization and avoiding heap allocations. So I started my career doing embedded systems in aerospace, and this is a pattern that's extremely common in embedded, and you don't really see it that often in more traditional backend systems. So I guess part one of the question is, why do you think that is? And then part two, it seems to me the benefits of these patterns are, number one, I think it allows you to more easily guarantee that you're sticking within a certain memory budget. It allows you to avoid heap allocations and preserve some better data locality. How would you proportion the benefit you get to those things? And are there any that you think I missed?
Yeah, no, that's great, Richard. So I never worked in aerospace and never got the privilege to do embedded, but I've always been a fan. I've thought embedded is where things are going, like also in gaming. And that's what kind of attracted me to Zig, is that there were so many embedded programmers and game developers coming to Zig. And I always thought that's a very good signal, very strong. The thing that drew me to static allocation was NASA's Power of 10 rules for safety critical code. And before TigerBeetle, I was working on a distributed system. It was a full duplex file sync, kind of like Dropbox, but proprietary. No one knows it. And it was an incredibly, incredibly hard problem to solve. And there were 3 versions of that system. Each time we thought, this is the one. This is the one. And each time, this is not the one. It's as reliable as Google Drive Sync was or OneDrive was. And in the end, there were 2 or 3 key things that made the project a success. And those learnings became what we call Tiger Style, which is the engineering methodology behind TigerBeetle for safety, and performance, which includes static allocation. So what it was these 3 things were firstly like assertions. So as your software runs within your function, you're checking what you expect. But you're also checking what you don't expect. So you're not only checking the contract, but you're checking for breach of the contract. Have we gone into breach? What we call this negative space. So you're trying to, if you think of it as linear programming, you're trying to, shade in and check that you're staying where you think you should be and you're not going into the negative space. Those are assertions. Another principle is like online verification. So while the program is running, you're not only doing like assertions within functions, but you're writing whole functions just to like read data out and check it and do bigger tests. And then anything goes wrong, the slightest thing you shut down. But the other idea was static allocation, which is not the same as, bring your own arena allocator. That a lot of people think that's static allocation. We're just, at startup. And actually, we think of, to be clear, we think of static memory allocation not in the embedded sense where, it's physically like at compile time. So for us, it's okay to do heap allocation. It's more the principle of static. So there are like known limits. But some of these limits might be known at compile time. Again, Zig comp time is great for this because you can do constants and, thread them through and even calculate them at compile time with Zig functions. So you have compile time constants, but your static memory usage at runtime might also be determined by runtime parameters. So the operator might want to say to the database, TigerBeetle, you are allowed to use exactly 16 gigabytes of memory, and that's it. So it's like C groups, but in your database. And that's a combination of comp time and runtime. So that's why we're okay. At initialization, yes, we can allocate on the heap, but thereafter, once you go into runtime, there's no more malloc or free. But the reason why we came to static allocation was because the real beauty of it, there's many advantages. So yes, it solves fragmentation. Yes, you can probably pick up like deadlock issues because now you've got assertions. So, and by the way, that full duplex file sync, it then was a success and it worked great. The other ingredient there that we had was also simulation testing, which we can come back to because it wasn't deterministic. So there were bugs that, it found bugs. There were bugs that took a year or 2. We knew they were there. They took a year or 2 to fix. So it found the bugs very quickly. Simulation testing, injecting faults into the system. It was full duplex file sync. So it would simulate like user operations, move things around, rename them, weird UTF-8 multi-byte encodings on NFC, normal, NFD, whatever, across Windows and Mac. And this tool could crash most of the file sync tools, except Dropbox, and in the end, except this one. So it really worked. The problem with that simulation testing was, it found bugs, but you couldn't fix them. They took 2 years to fix, and we did eventually fix them. One of them was a buffer overflow in libUV, which was, incidentally, this was many years ago, but this was some of the first C code that I ever wrote, was to fix a buffer overflow. But static allocation, sort of the motivation for that came out of security work I was doing, where what you found was hackers could often exploit a system. For example, there was something called a Better Zip Bomb by David Fifield. It won at the Workshop for Offensive Technology. There's actually a workshop for offensive technology, WOOT. And this zip bomb could take down Chrome and almost every antivirus, almost every system it could take down. It was like a 42 kilobyte file that could become 42 petabytes. And Fifield had found a way, using the scientific method, to make the world's most potent zip bomb. Again, power to weight ratio. And doing that kind of work, I happened to be doing a lot of static analysis work where it was actually coincidentally looking at the zip file format and just checking everything. If some program were to open this Office file, would it probably lead to buffer overflow? That's actually a very easy problem to solve. You don't need to rewrite Office, rewrite it in another language. You can actually use static analysis on the file format to detect what would probably be a memory safety issue. Often this is also checked arithmetic, where the file format is intentionally trying to overflow offsets and sizes. That's why checked arithmetic in safe builds is so important and why it should be on in default. Most languages have it off, just like they have assertions off in production, but it should be on. But static allocation, I saw with zip file formats and security, you really do want explicit hard limits, because if you don't, hackers are going to exploit that, whether it's through checked arithmetic, whatever. So I came at static allocation from this idea that explicit limits make for more secure software. And then with TigerBeetle was like spinning that coin around into Tiger style and like, well, security, look at it another way, you get safety for databases. A lot of the same principles work. So that's where we got static allocation and NASA's power of 10 rules for safety critical code. And they really work. Like they help you make safer software with higher quality. And we'll come to it, I guess, because you guys will know all about this too. But you can actually create higher quality software in less time with these ideas. But I think that again, to come to the point, the beautiful thing with static allocation is it's a forcing function for good design in your team. So I think a lot of the reason why people want a language that is memory safe is because, they're allocating memory all over the show at different times and in different places. Time and space, that breeds bugs, time and space, because humans are not good about thinking across dimensions of time and space as you move things further apart. Our brains find that very hard. But put things close together in time and space, we're pretty good. But things like time of check, time of use, classic vulnerability, it's exploiting this gap between time and space. But static allocation is another way of thinking, how do we get to memory safety? Because at startup, you centralize all your resource allocation. Do it in one place. It's, and then it doesn't happen again. So now any kind of exploit is limited to like a logical exploit. You're not able to do, code execution. So there's many advantages, but I think most of all, really to make the point a bit more clear, is that it's a forcing function for good design. Because you centralize all your resource allocation, you're forced as the programmer, when you are writing some kind of component, you can't malloc. So you have to have a very clear architecture. Initialization time, yes, now you get an allocator. You can't store a pointer to it. Allocate what you need, and you have a dinit function. But otherwise, at runtime, there's just nowhere to allocate. So you actually have to think, and this is why it's not arena allocation, because for every single data structure, you're thinking very specifically, how much memory is this hash table going to use? Is it allowed to even resize or not? Must it stay the same? How does that affect my linear probing or triangular probing, or my chained addressing, or are we even doing open addressing? So all these things, static allocation is forcing your team. Normally, you'd never think about this. So your software is kind of like a jumping castle. It's very dynamic, and it's got no hard shape. But with static allocation, you get this very well-defined shape, because it has to be. After startup, it's fixed. And so literally, you start your program and memory usage never changes. And then I think second order, you actually get more efficient usage, because now you're fine crafting all your fields for memory locality. So you might not have a very good designer on your team, but if you force static allocation, suddenly everybody is really thinking and designing, safer software. This is just our philosophy. There's other philosophies, so this works well for us. But static allocation, we would say, is easier, because you can reach for something dynamic quickly now. It's easy, but tomorrow it's really hard. So we've actually had cases where some dynamic slipped into like our REPL. It shouldn't have been merged, but it came in at one point. Later on, it really cost us. It took months. There were features we couldn't ship because it was dynamic. It was just a mess, and so we had to go back and like make it static, and then it got easier again. So it's sort of go slow to go fast, hard at first, but long term overall, it's just easier if you keep it static.
Absolutely. Oh man, the challenge with letting you cook is there's a lot there. We certainly see a lot of parallels with the customers. It's almost like there's a parallel to where the machine only reads ones and zeros, right? And in some sense, it's just electricity slightly differing at one point and another, right? But there are so many different layers of thinking that we can layer on top to make things more sane and predictable and understandable. And Tiger Style is almost a reflection of this at the design and sort of intention level, where if we adhere to these, I'm going to call these metaphorical ones and zeros, there's obviously more than one, but that gets you a lot on top that builds into all of these different scenarios. And we see this because correctness, or however you want to describe it, if the program does what it's supposed to and doesn't do what it's not supposed to, the at knock-on effects from a security perspective, from a velocity perspective, you're no longer building with the house of cards. All of that starts to compound upon itself and really becomes a bit of a virtuous cycle. Since you brought up Tiger Style, I have to ask a question, which is, what about Tiger Style was considered in inclusion inside of your framework here that maybe didn't quite make the cut? Or is there anything that you might add to it now, having talked about it and been living the dream for a little bit more? Is there anything that looks like it might be on the horizon for pillar number 4, turning I was going to say pyramid into a table, but I guess a pyramid doesn't have legs. You get the idea.
Yeah, we actually think of Tiger Style as like a tetrahedron. We even have a poster for Tiger Style with a picture of it on. It's a big orange tetrahedron. The three pillars are performance, safety, and user experience. A very predictable user experience. Piece of well-defined software, trustworthy building block, like you say, David. So it's like you're climbing a mountain, and the progress you've made is real, and you're not going to keep going down and climbing up again. You climb up and you make steady progress, and you keep going. But yeah, performance, safety, experience, explicit limits, which speaks to static allocation. But it's not only limits of memory; it's limits of how you work with we call them the 4 primary colors: network, storage, memory, CPU. And they have 2 textures, latency and bandwidth. So this is all kind of interrelated. You want your programmers to think not only of like memory usage, but disk usage, and how's my bandwidth and my latency. And then you shape your system in terms of these things. But are there any pillars that we would add? We've added a few little examples to like clarify points. So Tiger Style's also got some ideas on how to name things. And we've
you buried the lead on that one. Yeah, naming things. Can we solve that?
Yeah, well, part of the idea, like, so I got the importance of this from James Cowling, who was saying he got it from Barbara Liskov, that names are very important because they reflect whether or not you have a clear mental model. If you've got great names for things, and sort of what we do is it seems to come down to not mixing tenses. So if you've got like a status field, like an enum, and some of them are like present participles, and some are, I don't know what other tense, or a verb. Something's funny there because you're mixing stuff. So that's usually like a bit of an indicator. So usually what we find is like nouns and verbs. If you're going to call something a present participle, we actually had this in TigerBeetle in our consensus. In consensus algorithms have this thing called pipelining, which is like a performance optimization, where you start to replicate the next request while the current one is committing. And we were going to call it pipelining the field. And suddenly we noticed that in our team calls, we have these walk and talks where we actually stand up, we switch off the screens and we walk around. So we're not allowed to look at the code. So it forces everybody on the team to have like a mental model of like this invisible cathedral in their head, because you can't work with the team if you don't have the whole architecture in your head. But you're also walking and talking, so your brain is a bit more active. But we started noticing on our walk and talk that we were referring to this thing called pipelining. And this is now very awkward for like meta communication, because sure, it looks nice in the code, but you can't call the thing pipelining because it's not a noun. And suddenly we clicked, like, don't use present participles, use nouns, like call it the pipeline. And everything gets so much better. Now, in your metrics, you say the replica's pipeline is full or it's empty. And these are like the second order things of Tiger Style, where we've sort of little tips for how do you name things that'll make you also develop faster as a team or more clearly. And another idea is that you want to avoid overloading names. So if you're doing like a two-phase commit protocol, in the application, but you're also building on consensus, often a lot of the same terms are used. So change the names in different places so it's very clear, which layer you're referring to. Don't overload. Yeah. I think the biggest tip is we do something called most significant byte ordering of names. So if you look at like a database, many databases, you open their config file, you'll see most of the configs are like max latency, whatever, or min latency, or the qualifiers come first. But then when you look at the configs, a lot of the related, variables or constants, they don't line up in the source. So the most important thing, like the thing that really groups them, is last. And the first thing you see is max and min. So we switch it in TigerBeetle or Tiger Style. So you have latency underscore min, latency underscore max, or user requests count max. We start to put the qualifiers and the units in to make it very clear. And then suddenly, as you add more related fields, they all line up in the source, and you can now very quickly see, okay, these are together, these are together. Yeah, which is kind of, that I don't know if you saw, OpenZFS had a bug where they used, I think, was it P size instead of A size? And they violated one of the Tiger Style rules, don't abbreviate, say physical or say allocation size, make it, because if your qualifier is longer than A or P, the signal is worse, anyway. So these are ideas. It's all defense in depth. How do we increase safety? Let's name very clearly, explicitly, verbosely, but even change the order so that you see things that relate.
Yeah,
so
I haven't heard a lot about making sure
major pillars. Yeah,
I haven't heard a lot about making sure that our grammar is up to snuff in the source. That's a new one on me, but I'm going to give that one some thought, because my wife is an English major, and
yeah, so she will know haiku. Sometimes you need arbitrary constraints because they force creativity. All you want is, you just want programmers to be forced to think. Like it's such an arbitrary subjective rule. Like, related things. For example, if you're doing like a mem copy from, often in C it'll be src to DST or DEST. And now the two variables, they don't line up in the source, but yet they're so symmetrical, So then sometimes you get it like source written out and destination. And it's like also so many syllables. Now to communicate as a team, you would say destination, 4 syllables, instead of just saying source and target. And source and target, 2 syllables each, they line up in the source. It's very clear. So these are things that we do. And again, it's like we joke about it. Sometimes it's really like just haiku, but it's meaningless. But that meaningless constraint forces some human creativity, just to try and get really like clear names that you feel good about. Also that encourage everybody on the team to get the same kind of mental model that they feel is very simple. So you also want to not only write the code to be correct and fast, but, can you think about it? And is there a clear mental model? So names are very important. Yeah. Got that one's from James. So
I'm curious, following up on that, if you have any tips for designing software to operate in low or no observable environments. Like, does it just imply that your testing budget has to be that much larger to ensure correctness?
Can you clarify, Richard? Like, what would be an example for me and for everyone?
Sure. So, like I said, I started out doing my career in embedded systems, and I was working on air data systems that were going to be operating on aircraft that were designed to be in flight for like up to a year. And if something, went wrong with the software, you have virtually no way of finding out. So you need to guarantee that the software operates correctly, regardless of your ability to monitor that. Um, do you have any techniques? It seems like TigerBeetle is in a similar situation where you're handing, your software and your customers are running it themselves.
Yeah, yeah. So I think, I mean, it's similar and it's different, um, because we're not always hard real time. We're more soft real time. That's one difference. The plane doesn't necessarily crash. If TigerBeetle crashes, um, there. So how do you, like, if you have like a long running system, how do you ensure safety? Is that right, or what would be a better way to phrase the question?
I guess like, do you try and build like online detection mechanisms that are constantly running that are detecting if things go wrong and then you react to them? Do you build like subsystems where you can log arbitrary telemetry and customers can ship that back to you in some way or yeah.
Yeah, that's it. Yeah, so that's the online verification. We also got that from James Cowling. They did a lot of that in the Magic Pocket storage system at Dropbox when Dropbox migrated like exabytes from S3. They just built their own S3, and the reason they could make that a success was similar principles. Is this online verification, constantly scrubbing your data, checking various things. Is it as we expect? Is it? And also asking the question, what might we not expect? So do we expect this counter to be saturated? Should we ever get there? Or if we're trying to pull a number from a cryptographic random number generator, that's a 128-bit, TigerBeetle actually has an assertion that it's never zero, which is technically incorrect because the CPRNG could return zero. It's a valid value in the 128-bit range. But we kind of, thinking probabilistically here, what are the odds? And if it is a zero, probably it's more likely that the entropy is bust. If you're getting a zero out, and that's probably way more dangerous. So sometimes it's like choose the lesser of two evils. But this zero one was quite a cool one because the odds of a collision in 128 is never going to happen. But so how do we ensure, like, for long running systems? I think static allocation helps a lot, which is why, like, so many of these systems do it, because if you are going to have like a resource leak or deadlock in your system, you're probably going to find it in testing if you have static limits. But if you don't have static limits spec'd, then you can't test them. And so there's no way to know if there is deadlock or resource leakage, because it's just not part of your program shape. Your program has no shape. And so that's why it's so important to give it shape, because then you can test the shape. So you can test the program through the whole shape. Then it's a question, well, is our testing powerful enough? Our little robot, vacuum cleaner, can it dust all, get into the corners and into the combinations of state spaces or combinations of 100% branch coverage, which you guys will know a lot about. But that problem, before you get into state space exploration, the first question is, like, do we even have a well-defined shape? Do we know what the shape should be, let alone have we tested and explored that shape? But that's why at least, there's temporal aspects and spatial aspects. But static allocation actually brings both together, because you're thinking not only about how much memory I use, but what will the lifetime of that memory be, but not even in the context of a local system where a borrow checker would help, but across the distributed system. How do these systems together can you get into like resonance patterns where you actually have deadlock that a borochecker would never find locally because it's a property of the system as a whole, global system. So this is why these things are so powerful, I think. I don't know if there's other things we found, but it usually comes to like fail fast, crash, 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 because the sooner you crash, the slightest thing, you will help your tests find the bugs. The other thing is if you have a distributed system and you have assertions and they crash because of, say, some deadlock or resource exhaustion, the interesting thing there is because your system's distributed, probably you hit such a rare state and you crashed one of the nodes, it'll come back up again with a healthy state. And now your system is actually more available because one of the nodes crashed. That this is a benefit of like obviously there's other kinds of requests that will deterministically crash your program. Yeah.
For sure. So you said something interesting there. You mentioned we were going to come back to simulation testing and deterministic simulation testing. We're not going to rehash the basics. For those that are interested in that, go check out one of Joran's other talks, or check out our CEO Will Wilson's talk at Systems Distributed, which has a great fundamental layout of what the distributed simulation testing kind of vibe and mindset is. The thing I heard you say that I'm interested in exploring further is knowing the shape of your program before you apply some of these really powerful testing techniques like fuzzing and simulation testing and so on. We've had some of these powerful testing techniques for a while, but they haven't caught fire in the market and in the people's mindset kind of a lot. And I was wondering if you thought that understanding the shape of the program or any other factor may have an impact on that adoption, or what do you think is driving the adoption or lack of adoption of some of these different tools and frameworks that clearly can enable a lot of safety and velocity and a lot of other good things we want. But when I talk to people, I still feel a little bit of hesitation. So I'm wondering if you see the same thing and where you think it might be coming from.
Yeah. So thanks, David. So I think, like, I could say, just speaking for ourselves for TigerBeetle, if we hadn't done static allocation, it would have been fatal. There would be no company today. If we hadn't picked Zig, probably also, if we had picked C, would have been fatal. Like, it would have been a mistake. So Tiger Style has been, so to put it in perspective, normally if you're building a distributed database, it takes about, if you build your own storage engine, it takes 5 to 10 years to get it production ready. You might call it production ready earlier and you're still fixing data loss bugs a few years later. Or there's bugs you haven't found because you're doing manual QA. If you do a distributed database and you have a consensus protocol, again, 5 to 10 years, that's Martin Thompson, who's one of the real pioneers in replicated state machines with LMAX. That would be the estimate. And he would say, anybody tells you it's less, the thing though is that TigerBeetle, we built our own consensus and storage engine to much tighter tolerances than they typically are built, because we now not only trying to solve strict sizability, in a network fault model context, which is that's enough for Jepsen to break almost every database except Foundation DB, and we also are trying to preserve strict sizability while the network fault model is happening hard enough, but while Kyle Kingsbury of Jepsen is also moving bits of data in our data files around and corrupting every single machine. So the problem just became, significantly harder, it's dimensionally harder. And the only way we could have done this, that Jepsen couldn't break TigerBeetle like this, was because we used deterministic simulation testing. We could do, coming back to the, Richard, your question is, we could actually not only just do correctness as table stakes, we could even add fault models and say we're going to preserve correctness, but in 100 times tougher environments. So suddenly you're getting some new capability, but you're able to spend it again on advances that you wouldn't have been able to make because the climbing that mountain would just be too hard without the kind of in other words, it's a safety net so that you can be more dangerous. It's another way to think of it. But coming back to your question, David, then with TigerBeetle, we did all of this and we got to production in only 3.5 years with supposedly these much harder programming style of static allocation. Most people look at that and say it's easier to be, let me just use JavaScript, it will be quicker. Or some GC language. But for TigerBeetle, we did it the tough way, but it was quicker. It was 3.5 years to much tighter tolerances, like dimensionally so. And that was possible because of, deterministic simulation testing. So it's kind of like the company would be dead if we hadn't done DST. So we've got no doubt in our mind, and we wrote our own simulator, much like Foundation DB, but then we still knocked on your door and said, well, we would like to use your simulator as well to make sure that our simulator is also catching all the bugs first. But I think people are starting to move to this testing now, because kind of what we've realized is the hard part, the cost of developing infrastructure, these mission critical systems. It's not actually the coding time. The hard part is the testing time. Coming back to, that full duplex file sync I mentioned, you can do simulation testing and you'll know the bugs are there, but it'll take you 2 years to finally find and fix them. So I've heard of some database companies, they raise like a round of funding, hire 100 engineers to do manual QA, or you could have just designed the system to be deterministically simulated, and now you're not only getting better developer velocity, but you're finding the 2-year bugs, and you're finding many of them and fixing them, like 5 of them a day. So it's kind of, you've optimized the thing that takes long, which is the testing. Yeah.
Yeah.
What
If
are
you think
what are your
about the
thoughts?
design
Yeah.
and the implement and the testing cycle, and maintenance, if you really look at the whole total cost of the lifetime of this, where are we spending the most of the time, and where can we put the most emphasis in order to try and cut down on the entirety of it?
Yeah, exactly.
Sorry, Richard, go ahead.
No, I was just going to say, one thing I learned from our CTO, Dave Scherer. I've been working with Dave for close to 4 years now. And, Dave will often, tell you something very concise that is just like intuitively very obvious, but you're like, I've never considered that before. Like that problem statement is just very succinct and valuable. And one of the things that Dave has argued to me a lot is, if you want to move fast and if you want to ship like powerful things very quickly, like, you just have to constantly be working on reducing your iteration loops. And that's one thing I think that's super valuable with deterministic simulation testing. Because, I've worked at places where I'm debugging or triaging a weird race that you see like once or twice a year in production. And you just do not get very many chances to solve that problem. So,
Yeah, no, that's it. And I think this is the thing. A lot of people think of DST as being able to rewatch the movie deterministically. But it's what you say, Richard, like actually it's speeding up your actual test time, because what DST also lets you do is fast forward the movie instantly to see, does it have a happy ending or not? Okay, it has a happy ending. Okay, let's watch another movie. Or let's take this movie and use it as the recap, for the next one in the series, so you can start branching. But the fast forwarding ability, not only the deterministic replay, but the fast forwarding to get to the interesting, here's the bug. Now we found it quicker. Whereas if you were running like simulation testing in real time, it could take like 5 minutes, and now you've only got 5 minutes of testing time. But if you're doing DST, you've made your physical war clock time, you've made it logical. Now you can tick the second hand in a while true loop. So in TigerBeetle, we've worked this out. Our DST simulator can speed up time roughly like a factor of 700x. So 1 second, you've got 700 seconds of test time, 2 seconds, etc. And now you can run these massively parallel. And this is the real game changer, because you make your local CI really fast for developer velocity. You basically just investing in good tackle to climb the mountain, but you can now climb it very quickly and many routes. Yeah.
And that 700x is presumably an underestimate too, because presumably that simulation is in environments where faults are occurring at a way higher rate than they're occurring in reality as well.
Exactly. Sometimes we clamp the faults. We've tried swarm testing where you're running pretty much normal scenarios, and so it's important to get different distributions, not always to be entirely chaotic, but also just be realistic. But yes, so you are doing a lot more test time where the system's not making progress because there's so many faults. But I think here, this is the other angle. A lot of it is like, how do we do better state space exploration? And the other angle is, well, how do we also just have a more well-defined space to begin with? And then the other principle is, well, let's design the state space away even to begin with. So we want the space to be like well-defined, but also we want to shrink it. And then we want to explore it. And then we want to make sure we explore everything. So static allocation helps with defining the space, but how you think about interfaces and actually making them buggier in the beginning, where you cross the boundary from physical non-deterministic machine to logical machine and logical system, which is deterministic, designing how you cut those interfaces we haven't spoken about, but that can also help a lot with state space explosion. So another principle in Tiger style is at your function return signature, try and minimize the dimensionality. So you could return like an integer from a function, or you could return a Boolean. The integer's got more information, therefore it's going to be viral through the rest of the call graph, leading to more dimensionality. A Boolean is simpler, void is even better, because now you're starting to design, that explosion of state space away in the first place through the interfaces. Now we're really rabbit holing, but
there's only one way we go on this podcast, and it's down into the rabbit hole. Interesting. So, Joran, as I'm thinking about this, and I'm thinking about how it's influenced the direction of TigerBeetle, I'm wondering about the role of purpose-built specialization in this context. So, TigerBeetle, obviously, feel free to correct me, but I think I'm going to get the gist of this right, came about as a purpose-built database from a financial perspective. So rethinking some of the core primitives that went along under the hood so that you could remove some bottlenecks that occurred for traditionally designed databases, or I should say generally purpose-designed databases. I'm curious if you see this approach where you take this level of specialization to solving the problem occurring more in the future, or if you see any sort of limits to that sort of approach moving forward. I say, as Richard is very familiar with some of the efforts that we've been taking that look like a specialized database, because that's what they are, to solve some of the problems that we're trying to crack here. And I'm curious what you see in terms of the limits of that, Joran.
Yeah, it's a cool question. So I think we are going to see more of it. And the reason is because we're going to have better primitives and building blocks for building these systems and databases. So if you think of it, there was a point in time when I too was a Rails developer. And, that was like an eye-opening moment for me, that in 15 minutes you could build a product with Rails, the Rails way. And I think the way we've built TigerBeetle is much the same. So at heart, TigerBeetle is actually a distributed database framework that you can use Zig comp time. You can take the debit credit, the financial transaction state machine out, the business logic out. You can put another database product interface in the Iron Man suit and compile it. And now you have Redis, or you have Foundation DB, or you have something else, but with the whole framework of TigerBeetle. So, we have a second database internally. It's not called Pangolin, but yes, we definitely agree with that. But I also think historically it's true. So in our world, TigerBeetle is a transaction database or OLTP database. Most databases are for strings. They pride themselves that they can handle variable length strings. They are string databases. We pride ourselves that we are not a string database. We're quite happy to be good at counting with integers. We are an integer database, and that's what we specialize in. We do integers. We don't do strings. And if the string databases mock us that we don't do strings, it's fine. Who would want to count with a string database that's variable length? So we do integers, and TigerBeetle specializes in counting integers. and specifically where there's the problem of contention. So, you have supernodes, 14 million people trying to get Oasis tickets. That's almost an impossible problem for a general purpose or OLGP database to handle. For TigerBeetle, we can do 400,000 a second of those. It's no problem because of, we've reshaped everything in the interface. We don't have SQL rollouts across the network. We don't have that. So it's an integer database, but historically too, there's general purpose databases. That was all you used to have, was the general purpose SQL. And then in 93, I think it was Edgar Cott, he coined the term OLAP. He said, no, we're going to have databases specialized for more interesting analytical queries. And so today, even DuckDB is quite recent as a database. It's specialized, doesn't do OLGP, general purpose. It does SQL, but specifically for analytics. And so the whole internal database anatomy is different. It's columnar, it's not row, vector, execution. Everything is different, and TigerBeetle is the same. And so I can quite imagine that if you want to build a new kind of queue or sequencer, it makes sense that it would be specialized, because you kind of have these complementary, databases in your toolkit, and you have your analytics, you have your general purpose, you have your transaction processing. Yeah, and I'm sure there will be more, if history is anything to go by. At least we're going to try and make it happen, so. I think it will be easier also because we've got testing,
Sure. Surely we won't put our buttons inside the database and we're like, you know what we need? We need a database that speaks UI. Like that feels like that's going to be too far, right? I say with a question mark, surely knowing the answer.
Well, I don't know. Have you seen Space Time? They're putting the game engine in the database.
I have seen Space Time. I've spoken to the team. Great team, yeah.
Yeah, I met Tyler in person, recently in Amsterdam at Systems Distributed. So I think that it's and I think this is kind of what we're getting at, is that the hard problem is not building the database. The hard problem is the testing. If you have deterministic testing, you can build new stuff, but you can also specialize stuff quite easy. It doesn't matter anymore. Why generalize when you can specialize? Because specialization becomes cheap. And I guess there's some point at which, kind of like evolution, you go back, you flip-flop between the two. But there's many specialized fish in the sea. And I imagine it'll become more and more true as that becomes more possible and cheaper.
I guess one kind of hot take I have is that amazing software performance is, let's say, underappreciated by the industry at large, especially for increasing software, especially for increasing product stickiness and user delight. Do you think I'm off base here, or do you think software performance does drive business fundamentals as well?
Oh, it absolutely does. And I think the question is, there's just, is it incremental or exponential? And when, if you've got something that's maybe a 2x change, people might not notice. 10x change, people start to notice. 100x, people really notice. 1000x, this gives people goosebumps. This really changes things. And I think kind of, if you look at Apple, they've always done this. So the screens, I don't know if they did 286s, but if you took the monitor of your old 286, the shape of it, roughly, the dimensions, they've changed a little bit, give or take. But the pixels have become so much smaller with Apple's Retina screens, which even are pretty old these days. But the pixels are so much smaller, you've got higher resolution, and that's possible because of performance, because the systems behind these pixels are able to drive that kind of display. So you get a high quality graphics display because of performance. And I think the same is true in databases. In our world, the world's becoming more transactional. People are transacting more frequently with smaller transactions, so you get more resolution in what you can do. So for example, you would fly somewhere and book a rental car. And that's one transaction, and it's quite a big transaction because it's for your holiday or your vacation. These days, you don't do that. you now, instead of one big transaction, that's less flexible, less resolution, because now you're stuck with your car. Maybe you want to jump on the plane. Now you can't do that. Jump on the train, go from Italy to France. You can't do that really because you're stuck with your rental car. Now you've got to drive or whatever. You're far more free because you can do ride sharing and Uber, and you just book the trip as you need it on demand. So things move from CapEx to OpEx, but you're getting more resolution, but there's more transactions and they're smaller. Or Airbnb, you might have your house, you would let it out, and you have to let the whole house out or you don't do it at all. And then Airbnb came along and says, well, no, just let one of your rooms and just for one night. Suddenly, accommodation became far more transactional. And all this is only possible in a business context because you got more performance. You can handle more of these transactions. It's smaller value, higher volume, and in these examples that I've given, it's literally 1,000x increase in transaction volume. So if you want to have business models like this, you need way more powerful databases. So actually, it's not a coincidence, but Airbnb, Uber built their own ledgers to handle the volume because the volumes were so much higher. And then the same is true for cloud. We used to buy servers, co-locate them for 3 years. It's one transaction for a Dell server for 3 years. These days, it's like serverless, and you're transacting per second as you use things, whether it's on or off. And as a result, there's new opportunities for businesses that didn't exist before. So all, performance enables business and business demands performance. So I don't think anybody wanted slower, buggier software. I think we've dealt with the bugs. Now we're dealing with the performance here, but performance is absolutely at TigerBeetle, we just keep investing in it relentlessly. More performance, more safety, more predictable experience. That's all we do. We just keep going on it because it will always be valid and important. You can also trade performance. You can trade it for cost efficiency. So you could buy a $4,000 machine and run Postgres and do 12,000 transactions a second, or you could get a Raspberry Pi with TigerBeetle and do 10,000 a second with a micro SD storage card. Not that you should do that, but now more things become possible. So I just love performance. I think the world needs it, but I also need it. I feel.
Do you think it creates any sort of incentive hazards? Because I let's just say I know people who, not me. Let's leave me out of this. As soon as something becomes performant enough to where I can be an order of magnitude more lazy, I tend to grab it very hard.
Yeah.
Does that concern you at all in terms of the chase for performance, or it's this is the cost of making things that are great?
I think it's the same with testing. The more powerful our testing, the more dangerous we climb. The more advanced things our software is going to do. And I think we kind of have to. It will happen. I don't know how one stops it. So we always like to say, be efficient and tasteful, not lavish and wasteful. I hate waste. I would hate it that someone takes this performance and wastes it. But for the people that do, others really do need the performance. And so I think this is, as a team, we sometimes talk about this, let's just fulfill our duty. Let's not cut corners. Let's build high quality software. We'll make good on our duty. How others then use that building block, well, that's their duty. That's sort of that's the best we could get it. I don't know how else. What
Clear
are your
separation
thoughts,
of
David?
concerns, perhaps.
Maybe.
Yeah.
What are your thoughts there? Is it something we could be doing?
I think there is only so much of the world you can bite off at one time. And the more stable pieces and the more performant pieces that we create, the better building blocks that others focused in other domains can create. So if we improve our practices such that software and systems no longer feel like a house of cards, or no longer feel alive in the bad sense. There's an alive in the good sense, and then there's alive in the it's out of the cage kind of bad sense. So the less we can do of that, I think that actually creates more room for more good things to happen. And personally, I'm an optimistic guy, Joran. So yeah, people will do good things, and maybe there will be bad things, but we'll fix that later. That's That's a problem for future us to figure out.
I'm pretty positive too. So I that resonates.
Yeah. Well, Joran, is there anything else you'd like to leave the audience with before we wrap it up here today?
No, well, I just think, if anybody's not doing DST, it's existential. They need to jump on it. So it is a game changer. And yeah, I think these other techniques of Tiger style, also can amplify that. But yeah, thanks to you guys and the team at Antithesis for always being awesome and pioneering the way through Foundation DB, and now, taking this magical elixir and holding it out for everybody to drink from and create immortal, high quality software in infinitely less time. So yeah, kudos to all of you, what you're building, that magical deterministic hypervisor, and yeah, appreciate always, all the energy there.
I think we need to update our company motto.
There we go. Yeah, and likewise, thank you, Joran, because it is the way that you guys are developing in public, I think, is truly admirable, and it is always a privilege and a pleasure to get to hear a little bit of your thinking and how you guys are understanding everything that's going on here. And for those listening, thank you so much for listening today. And I hope you guys otherwise have a great day and enjoy the conversation. Take care.
Thanks, guys. This was great.
Thanks for checking out the Bug Bash podcast. If you want to reach out, maybe with an idea for the show, or maybe you want to be on it, send us an email at bugbash@antithesis.com. Or if chat's more your style, head over to antithesis.com and scroll to the bottom, where you'll find the link to our Discord. Until next time.